Let's talk about regular languages. So we've been doing these induction proofs for a couple times, but like I said last time, that this is actually, we're not going to be doing those, every day for the rest of the semester. I want to talk about something a little different today, which is a little more down to earth. This is what we call closure properties for regular languages. And I will say pretty shortly what I mean by closure properties. The idea here is, remember, a regular language is just some language which can be the language of a DFA. So all of the DFAs that we've talked about so far, their language that they accept is a regular language, and that's what it means to be a regular language. It's the language of some DFA. And the question concerning this topic of closure properties is something like this. If, let's say, L1 and L2 are regular languages, so you can imagine these as being just the two languages associated to two different DFAs, then you can ask something like, is L1 intersect L2 also regular? Or you could ask the union, right? L1 union L2. L1 and L2 are sets. That's what a language is. It's a set of strings which are accepted by the DFA. And so, since they're sets, you can try to mix and match them using your typical set theory questions. Now, this sounds like, to me at least, as written, sounds like a very abstract question. If L1 and L2 are each regular languages, is the intersection also a regular language, or is the union also a regular language? They are not so, this is not like a purely, insanely abstract question, though. Really what it comes down to is sort of like, if I have two different DFAs that have these two as the languages, you could ask, is there a DFA which accepts all the strings from here and also from here? Actually, that's this, the intersection, right? Because I said and, right? And that's what and means for the intersection. So if I have another way to think of this, so in terms of machines, the same question can be phrased in a way which maybe seems a lot more down to earth. In terms of, let me just say DFAs. Here's the same question. If I have two DFAs, is there a DFA which accepts only strings accepted by, let's say, machine 1 and machine 2, right? That's the kind of thing that really we are talking about. If I have two different DFA machines, I could ask, is there some way to combine those two machines together to make a single machine which accepts only when those two machines both accept? That's why I said the word and. Or you could ask a similar question, what happens, is there a DFA which accepts only strings accepted by M1 or M2? That's another question, right? And these two questions are really equivalent to asking these questions about intersections and unions. So this is just two different ways of saying the same thing. And this is really about sort of starting with two DFAs and somehow combining them together. Maybe you can imagine chaining them together in some way so that what you get is another machine which accepts either the intersection or the union. All right? The answer to all of these questions is yes. So it is a fact. If L1 and L2 are regular, then the intersection also is regular. That means, another way of saying that is, if you have two DFAs, then actually it is possible to somehow chain them together in some way to get a DFA for the intersection or for the union. So I will, and we're going to talk about why that is, but for now I will just tell you sort of a little spoiler alert. The answer is yes, that is to say, if L1 and L2 are regular, then L1 intersect L2 is also regular, right? This is a theorem. which we're not going to do like an abstract proof of this, but by the end of today, you'll understand why this is true. Anyway, this is why this is called a closure property. So the way, a fancier way to say that is the regular languages are closed under intersection. I hope you all are familiar with this language we use in mathematics every so often. Like in your linear algebra class, you talk about like a subspace or something which is closed under addition and scalar multiplication. Closed under addition means if I have two things that are in there and you add them, the result is also in there. And this is what we mean by closed under intersection. If I have two things that are regular and I intersect them, then the intersection is also regular. So this is, that's why everything that I'm talking about here is referred to as closure properties of the regular language. And the big sort of overarching question is, if you start with regular languages and you try to like recombine them in some way, then is it still going to be regular? Those are all about closure properties. All right. We are going to talk about intersection and union, but maybe as a little warm-up, and this is actually much easier to discuss than intersection and union. There's another set theory operation that's even easier to discuss, and that is complements. This is a simple operation from set theory, and in our book they use the bar for complement. So I'm going to write, S bar for the complement of S. Anybody remember what does the complement mean? Any discrete math wizards? You don't have to be a wizard to remember. Yeah.
Isn't everything outside of the set that's not in the set?
Yeah, everything that's not in S. That's what S bar means. S bar for the complement of S, and this is, you could say S bar is sort of the set of all X such that X is not in S. All right. In abstract set theory, usually you have some kind of like a universe. You could say the S bar is something like U minus S if you have a universe, although we usually don't talk about. If you want, you could say S bar is sigma star minus S. In our context, S is a subset of this sigma star, remember, refers to all possible strings using the alphabet sigma. S bar means all the strings which are not in S, all right? So the question is, if I start with a regular language and I take the complement, is that also regular? And I think we can just talk sort of by way of an example about that. In terms of DFAs, now this is a weird DFA. I don't even know what the language is necessarily. I'm just trying to make up a slightly complicated example, I suppose. All right, that's a DFA. Let's say, call this language L. All right, let's say L is the set of strings which are accepted on that DFA, and I'm not really even going to try to say exactly what those strings look like, because it doesn't really matter for the sake of this example. Could we make a DFA? So can we make a DFA with language L bar? That's the question. All right. This would be a DFA where the stuff, the answer is yes, we can. I'm going to draw a new DFA over here, and the point of this new DFA is it accepts only the ones that this one does not accept. Anybody, it's not so hard to describe in words. How would I build, using this diagram, somehow change it around somehow so that it just accepts the opposite? Any suggestions? To accept the complement. Yeah?
You just swap the accepting states and the non-accepting states?
Yeah, right. I'm just going to draw exactly the same diagram, except he said swap the accepting and the non-accepting states. So that means the two states that used to be accepting, I'm going to make them rejecting now, and the original state which was rejecting, that starting state there, I'm going to make it accepting. All right? So the answer is yes. How exactly did I do this construction? We swap the accepting versus rejecting states. and leave all the arrows as is, right? And this demonstrates that if you start with one language over there, you can make a DFA for the complement, and that means if your original language is regular, then the complement language is also regular, because all that regular means is that there is a DFA for it. Okay, so that means, and I'll write this as a theorem, although I don't think we need to talk about the proof. It means if L is regular, then L bar is regular. If you want to be fancy, you can say regular languages are closed under complements. That's what this means. But I'll just say it this way. If L is regular, then L bar is also regular. And if I show you a DFA for L, it's easy for you to draw me a DFA for L bar. You just, like I said, you swap the accepting and rejecting states. All right? The rest of today, I want to talk about intersections and maybe unions. So we would like to do a similar kind of procedure for intersections. You can tell right away it's going to be a lot more complicated, though, just because if I intend to do intersections, that means I start with two things and somehow combine them into one thing. So it is going to be more complicated than this. This just starts with one thing and gives you another one thing. All right, but let's talk about intersections first of all. Once we understand the intersections, actually it's not so hard to, like the intersections and the unions are quite similar to one another. So let's talk about intersections first. All right, let's just do an example here. How about L1 is the set of all things that look like a to the n such that n is even? As a sort of warm up here, I'm going to do a very simple example where the alphabet is just A. So no, not A's and B's, but just A. Just to do an easy one to begin with. Let's say L1 is all even length strings on A, and L2 is going to be all multiples of 3. So I'll say A to the n where n is divisible by 3. All right. So first I'm going to draw a DFA for each of those. And our goal is we want a DFA for L1 intersection L2. All right. Intersect means, of course, it means that I'm talking about just the strings which are in both L1 and L2, right? That's what intersection means. So let's draw our two machines for these two things. I have, first of all, for L1, I'll call this one M1. This is the machine which gives you L1. This is just even versus odd, so I hope everybody remembers. This is like one of the first examples that we ever did. It's just that, right? This will accept any even length, and I'm just using single letter for the alphabet here, so we don't have to draw any B's or anything. All right, that's the M1. Anybody recall, how do you get the other language? I want n to be divisible by 3. Maybe just for fun, I'll give names to these states. I'll call this one E and O. Is that confusing to use the letter O inside there? It's not an accepting state. I'll make a fancy curly Q O. Even and odd. That's what the E's and the O's are for. What about the other one? Can anyone remember how to do this? Only except if it's a multiple of 3, divisible by 3. They don't want to say it. Yeah, make 3 things kind of in a cycle. And if I want divisible by 3, then it's the starting state which should be accepting. All right? And maybe I'm going to give names to all of these. Maybe I'll just call these X, Y, and Z. All right? And here's the big idea. So the big thing is we need a DFA which somehow combines these two together. And the idea is our I'll say our DFA for the intersection must kind of do both simultaneously, I have suggested that maybe you would want to chain them together, but you can't really do one after the other. These are not sort of big, long things that you can just plug the end of one into the beginning of the other one. It's more like we are trying to look for a DFA which accepts everything on this one and this one, which means you kind of just have to like do them both at the same time. This is the basic idea. We must do both simultaneously, and this is referred to as the product construction. And it's called product. Product in the sense of set theory, not like multiplying numbers, but remember the product in set theory is the set of all pairs, one thing from the first thing and one thing from the second thing. So this product refers to the product in set theory, and our states will be pairs. That's how this works. All right. So the original states are E and O on the left side and X, Y, Z on the right side. The machine that I'm going to write has 6 states made up of all possible pairs. And you can write these down however you like. Maybe I will do it, say, E comma X, that's one pair. There's E comma Y. I'll put all the E's across the top. EZ. And then I have OX, OY, and OZ. All right? These are all possible pairs, one from the first machine, one from the second machine. If your DFAs are really big, then this will be really, really big. So we're not going to try to do really, really big ones. All right? These will be the states. And the purpose of this machine, the idea of it is to do both of those machines up there kind of simultaneously. So we need to decide where should the starting state be, and I'll just tell you how this goes, and then we'll do some more examples. The starting state shall be, I think it only makes sense, to make the starting state E comma X, because those are the original starting states from up here, right? The E and the X. So E comma X will be our starting state, all right? Let's draw the arrows, and then we'll talk about accepting states. Let's draw the arrows. So the state from, or the arrow from EX, which is labeled A, we only have labels of A this time. Sorry, I never wrote labels on this one up here. These guys should all be A's. Anyway, E comma X. Where does the arrow go with an A? Well, if you're trying to do both at once, you just think about where does the arrow from E go and where does the arrow from X go? E goes to O, X goes to Y. That means E and X goes to O and Y, like that. Right? So I'm looking at both things in the pair, and you just do that arrow on both individual things and see where they go. All right? This is not so hard to do once you know what's up. Okay, remember, I have only one letter here, A, so every state needs an outgoing A. So let's look at E and Y. E goes to O, Y goes to Z, so that means E and Y goes to O and Z, like so. E and Z, E goes to O, Z goes to X, so E and Z goes to O and X. I'm going to have to cross the lines over here, I hope you don't mind, like that, right? E and Z goes to O and X. Okay? I did outgoing arrows from all the 3 on top. Let's do the ones on the bottom. O and X. O goes to E, X goes to Y. So O and X goes to E and Y. That's there. O and Y goes to E and Z. That's there. And O and Z goes to E and X. That's there. All right. I think I did those right. This is a little messy because I crossed the arrows over. You could actually kind of rearrange the states, untangle the picture so that the arrows wouldn't cross anymore. But this is what we get. All right. The idea is you're doing both DFAs simultaneously. And we should decide what should the accepting states be. You have to remember what we're going for here is the intersection. That is, it should be accepted here if it was accepted on both of this one and also this one. So what that means is, in order to be accepting in the product machine, both parts of the pair should be accepting on the original two machines, which means E and X should be the only accepting state over here. E and X should be the only accepting state. All right? And this is the answer. This is actually a DFA which accepts the intersection of those two. And if you're, I don't know if you can untangle the lines yourself. Really what this is 6 states which are all in a big loop. You can't tell because they're all sort of drawn on top of one another, but you can go EX to OY to EZ to OX to EY to OZ back to EX. That's a loop, 6 states around in a loop. That means this will accept anything which is divisible by 6, which if you think about it, that is exactly the same as saying it's divisible by 2 and also divisible by 3. That's the same as saying divisible by 6. So I feel pretty good about this. Let me just describe, I hope that everybody gets it. Let me just, for the sake of having it in writing in the notes, can we describe what the ingredients here are? First of all, the states are pairs. States are pairs, right? From each of the 2 original machines. What about the arrows? So the arrows simply do the transitions from each element in the pair. Maybe I should say, instead of element, probably it's more appropriate to say coordinate. That's how we describe ordered pairs. What I mean by that is, for instance, what should I do for the arrow from E comma X? It means you look up the arrow from E in the original diagram. You also look up the arrow from X in the original diagram, and you do whatever that says. So that's what I mean by you simply do the transitions from each coordinate. You look at each of those 2 things separately and see what happens. All right? The starting state, we should say what that is. So the starting state is always just the pair of the original 2 starting states. In this example, the original 2 were E and X, and so that's why this starting state is E comma X. So the starting state is the pair of the original starting states all right? And finally, the accepting states are ones which are accepted on the first one and also accepted on the second one. So maybe I'll say it sort of this way. If I had something like A comma B, this is accepting if A and B are both accepting in their original machines. This is how we do, and this whole thing is called the product construction because you are making pairs of states from the original two machines. All right, and it's not so difficult to do once you know what you're doing. I got one more example, and then I have one for you all to try. So let's try one with A's and B's. This was kind of a simple one because it was just A's. Yeah, you got a question?
Would it be all right if I leave class early? It's kind of an emergency.
Yeah, sure.
I can email you slide after.
All right, if you want.
Sorry.
Yeah, no problem. Okay. I hope everything's all right. Let's try another one. All right. This one's going to have A's and B's. So how about AX, where X is in AB star? So that just means all strings which start with A, and then after A and then something, where the something could be anything. And then my L2 is going to be all X such that X has an even number of B's and any number of A's. All right? These are the two languages I want to start with. Our job here is draw a DFA for the intersection. All right? So this involves, first you make two DFAs for each of these, and then you combine them in that way that we just did. All right? So your job, make a DFA for L1 intersection L2. All right. We should first draw the DFA for each of those individually, and then combine them together using the product construction. So let's make a DFA for each one individually. AX, that means it starts with an A and then has anything else. That could look like, I'll call this M1. We've done this example a couple times, I think. Something like this. It starts with A and then anything else that will be accepted. If it starts with B and then anything else, that's rejected. So it's like this, right? That's the first one. And then my second one, I am going to say an even number of B's and any number of A's. Remember, whenever it's about sort of evens versus odds, you basically want two states going back and forth. And since it's, so this is my second one, about the even number of B's. So it's like this, B, B, like so, right? That's an even number of B's. And to make it even, I make the one on the left accepting. Any number of A's. Anybody can say, how do I incorporate that? I want to add some A arrows, make it so that you can just have A's whenever you want that don't really affect anything. Yeah?
They would just loop both of them.
Yeah, yeah. Each state here gets a loop with the A. Great. So here, doing the A's has basically no effect. So you can have whatever A's you want, but the B's has to be even. Excellent. All right, let's see if we can put them together using the product construction. Now, maybe I should have done this before. I should have names for all of these states because I'm going to have to make a bunch of pairs, right? So I will call these on the left maybe ABC. Sorry, the labels are a little small. And on the right, I'll call them S and T. Whatever, you can call whatever you want. All right. Now, in this example, again, we have 3 states on the left and 2 on the right. That means the total number of pairs will be 6, right? There's going to be 6 total pairs. Although I would suggest I'm not going to write down all the pairs to begin with. So here's a little kind of, I mean, you certainly can, but this is a little life hack. Start at the starting state and then just make new states as needed. You're going to see actually, like in theory, there are 6 total pairs that you could make, but actually some of them are never going to actually occur when you're doing both machines simultaneously. You'll see what happens. Anyway, I am going to begin with the starting state, which is A, S. Right? That's my starting state. And let's just say from there, I need an arrow with an A on it and an arrow with a B on it. What should my A arrow go to? So I'll put it like this. Actually, in theory, it could loop also. But my A arrow, I say big A goes to B and S goes to S, right? So that means A, S should go to B, S. That's because when I do A becomes B and S becomes S. All right? What about AS with a B? I need an outgoing arrow with a B on it also. With a B, I see A becomes C and S becomes T. So AS goes to CT. I'll just put that one down here. All right. If you sort of draw the states as needed, you will avoid a lot of extra lines crossing. And actually, there are many states that you may not even have to draw at all. All right. I'm feeling good so far. How about arrows from BS then? The A arrow, anybody want to say? Somebody shout it out. If I'm at BS and I do A, where does that go? I saw someone giving me the hand signal. It looks like this. It's a loop, right? B goes, you should be looking at the A arrow. B goes back to B, S goes back to S. So BS goes back to BS. What? A. With an A, right? What about with a B? B stays a B, S becomes T. So when I do the B arrow, BS goes to BT. And I'm going to put that one over here. I already drew this on my paper, and I did it in a way where the lines never cross. I don't like when the lines cross. It's just, I'm just quirky like that, I guess. All right. Okay, let's continue. So you just have to keep drawing arrows until you have finished the DFA, which is to say every state needs 2 outgoing arrows, an A and a B. So from BT, the A arrow, B goes to B, T goes to T. So the A arrow is a loop here. And the B arrow, B goes to B, T goes back to S. The B arrow, BT, goes back to BS. So it's like so. All right? So actually, I don't need any new states over there. What about BS? I already did BS. Okay, what about C and T? I need 2 outgoing arrows from here. C, let's do the A first. C goes back to C, and T goes back to T. So the A arrow is a loop here. And the B arrow from CT, C stays as a C, T goes to S. So that actually goes to CS. That's the B, all right? Sorry, I'm off the bottom. Now I need 2 arrows from CS. The A arrow goes C back to C, S to S. So the A arrow is a loop. And the B arrow loops at C and goes across to T. So the B arrow does that. And now I think I'm done. I mean, I'm done with the arrows, right? You'll notice there's only 5 states here. That there's one that I never even drew, which is A, comma, T. Apparently, like, if you're doing both of these machines at the same time, there's actually no way to ever get to A, comma, T, because that would require a B first to get to T, but a B first will make you C. So you can't ever see A, comma, T. In larger examples, it's possible that there could be many, these are called, the book calls them like inaccessible states, and you don't need to bother drawing them in your diagram down here. All right? I think there's one last thing we need, and that is to indicate which are the accepting states. Remember the rule for that. Since I want the intersection, the accepting states should be the ones which are accepted here and here. That is B, comma, S is the only accepting state. Like that. There you go. This is my DFA for the intersection. All right. Any thoughts about that? This is hard to think through, but apparently what this means is this DFA will accept anything which starts with A and has an even number of B's. And I mean, that's not so hard to see, right? If it starts with A and then this makes an even number of B's, it really does work. If it starts with B, it goes down here. I mean, it could go back and forth if you like, but this is all failures down here. All right. Looks good to me. I got one for you all. See what you think about this here. This is another one where you should not try to draw all the states at the beginning because there's going to be several states that are unreachable. This is a somewhat complicated DFA here, and I don't, you actually don't have to think at all about like what exactly are the strings that are accepted on this one. It doesn't really matter. You can just do the product construction even if you don't really understand which strings are accepted. Okay, so that's the first machine, and the second is going to be similar to the one I just did. This is 2 states. Somewhat weird arrows there. All right, see what you think. Put them together using the product construction. Is anyone confused that there's 2 outgoing B's from state C? Sorry about that. I don't know what did I mean to write? I don't know what I meant. That's what it says on my paper also. This is illegal to have two B's exiting from this state. Can we just get rid of this one? Sorry. So from C it goes to D with the letter B. Sorry about that. I hope I didn't do that elsewhere. I think the other ones are okay. Oh yeah, there's 2 outgoing A's also. What was I thinking? Okay, it looks like, yeah, I'm sorry about this. I don't know what I was thinking. On my paper, I did it this way. So take away this. There used to be an A here. Take that A away. Use the A going up. Sorry about that. I hope you didn't get that far yet. I'm going to start drawing my answer. When I did mine, I only used 6 states. Although, I don't know if you trust me. I don't know if I trust me. What I had on my paper, I only ended up using 6 states. If you find yourself using more than 6, you may have messed it up. Maybe you drew the same state twice. Or maybe I messed it up. All right, I'm going to write down the rest of my answer here. Unfortunately, if you mess it up sort of early on, it can screw the rest of the whole thing for you. C S. C and S. Maybe we can talk about these sort of as I finish. So far I have this much. I hope that you agree with me so far. I'm now doing the arrows out of CS with the A. C becomes B and S becomes S. So CS goes to BS with the A. That's here on my picture. And with the B, CS goes to C goes to D, and S goes to T. So CS goes to DT, which is here. Those are my outgoing arrows from CS. Now my picture is almost done. I just need outgoing from D and T. The A arrow from D and T goes D and S. And I don't have that here yet, so I have to go D and S. That's an A. D and T with a B goes D and T, so that's a loop. And then D and S, I need arrows, and hopefully I won't have to make any new states. D and S. The A goes back to D, the S goes back to S. So this is looping with an A. And the B, D is a loop, S goes to T. So this goes back that way with a B. And I think I'm done drawing my states now. I hope that you got something like that. This is complicated enough that it's hard to tell maybe if yours is exactly right. Although if you have more than 6 states, then I think it's not right, because I think this is right. But at a certain point, like, I'm not any better at doing these than you are. You just have to make sure that every little arrow is exactly right. Anybody have questions? I mean, it certainly seems to me that everybody understands the procedure. You may mess it up from time to time, but it's not such a difficult concept. Anyway, what are the accepting states? Remember, since I'm doing the intersection, it should be accepting down here if it was accepting on the original in both coordinates. So accepting should be A, comma, T, and also D, comma, T. Those are the only pairs which are accepting on both. Now, actually, I never drew A, comma, T, but DT is down here. That is an accepting state. And it is the only accepting state in this example. All right, I think that's what I got. Any questions about that one? We got 5 minutes. Actually, this is enough time to briefly talk about the union. Maybe we'll do a full example of the union next time, but this is a DFA for the intersection. Actually, it's very easy. I mean, it's the same basic procedure, but it's a very easy modification to get the union. So, to get the union instead, can anyone suggest how would we get the union instead of the intersection? You have to just think about there was only like one thing where we even cared about the fact that it was intersection at all, and that is the fact that down here I choose the accepting state to be things which are accepted here and also here. How would I do union?
It's or.
Yeah, you just do the same thing but use sort of or. So to get the union instead, the only difference, like it's the same diagram with the pairs and the arrows. So do the same product style diagram. The only difference is deciding which states are accepting at the very end, and you do the same way but you use the word or instead of and. So do the same product diagram, but the accepting states, and this is the different part, the accepting states are ones where one coordinate, by coordinate I mean like each pair has 2 things in it. Those are the coordinates. One coordinate or the other, or both, of course, that's included in what I mean as or. One coordinate or the other are accepting in the original machine. Machines, I should say. All right. So for that example up there, we don't need to redo the whole thing. Really, all it's about is taking this diagram, and I'm just going to, sorry if you're drawing on paper and you can't copy and paste like I can. Move it down a little bit more. So here for the union, it would be, so this time I want, it's only a matter of which are accepting. And actually in the union, that one which was accepting before, it still should be accepting. Like it was accepting because both of them were accepting, the D and the T. Is it true that the D or the T? Yes, it's still accepting. But I should go through the other ones. And really what it comes down to this time is, on my original machines, A, D, and T are accepting. And so on my product machine, with the union, anything with an A or a D or a T, all of them should be accepting. So any of these states which have A, D, or T, that would include this one, or this one, or this one, and I think that's it. Those are all the ones. These are all states. I mean, all pairs, including A, D, or T. Those are in parentheses. All right? Many more accepting states than before. And I think that will just about do it. Maybe we'll do one more example with the unions next time, but this is the basic idea. All right, next time we will have our quiz as usual. It's based on the stuff that's on the homework due tonight. So let me know if you got questions.